All right, today I'm going to do one problem before I get into inductor transients for you of your choice. Which one was it? Which one would you like? Didn't somebody want me to do a problem? Or not? Yeah, which one?
I got a question for define the K1. So it's like the K1 in the in that equation is defined by when the t less than the 0 seconds and the voltage.
Why don't we put the equation up and show you how it's relative to this? Because I think everybody needs to know exactly what you're asking. He's saying if we're talking about RC problems, when we have an equation Vc of t is K1 e to the minus t over tau plus K2. We know K2 is the voltage, is V across the capacitor as t goes to infinity. We've established that. We know tau is really R Thevenin times C. And all this is pertinent for t greater than 0, right? And that's, y'all with me? Can you all hear me in the back, far back? All right. So this is the voltage. K2 is something we look for as the final state of the capacitor in terms of voltage. The way we get K1 is we look at t equals 0. And at t equals 0, we know that the voltage across the capacitor at t equal to 0 will be equal to K1 plus K2. Reason being is because at 0, e to the 0 is simply 1, isn't it, class? How many see this? So therefore, K1 plus K2 is the voltage across the capacitor at 0. Or you could say K1 is equal to Vc at t equals 0 minus K2 if you want. But it doesn't matter. That's the equation. That's all it is. All right. Did you have a problem you wanted? No? Yes. Say it again? 333. Did we do 333 before? I think we did that, didn't we? Well, 34 is the one I gave you, right? That's the one I thought I'd get asked. Yes, sir.
You showed 324.
Yeah, I'd be happy to. But this is your last problem. So you want 324 or 334? Either one.
Let's go with the harder one.
Can we get one similar to like Quiz?
Sure. That would be everyone, right?
We just change the resistance.
334.
334 is a good one. Why is it tough? Anyone? Final voltage isn't 0, right? How many looked at 34? Y'all should have. Wasn't it homework?
You said
24. Pardon?
You said 24 on the.
Or 24. It's 24 or 34?
You said 24 on the.
Okay, we'll look at it. It's the one where the voltage doesn't go to 0. I think I forgot the number on that one, but I'll take a look.
Yeah, that was 34.
That is a homework problem, right?
What? 34.
Okay, it isn't? I thought it was, but that's okay.
Well, let's do that.
24 goes to 0, but we can do that. We can do 24 fairly quickly, and then we'll do 34. All right, this is the problem. Let me just mention something about this to you. Really, by this time you probably are seeing what this really boils down to. Is something where you look, if the final state of that capacitor is 0, then the circuit that's around that capacitor is just the circuit that charges it up. That's all it is. Do y'all follow me, class? That's it. So if you look at this problem, for t less than 0, you got 12 volts, and I'll put it up here, plus the minus 12 volt source, 2K, right? Then you got 6K. Then you got 12K. And then you have the capacitor, and I want this voltage. Right? Y'all see this, class? I've just redrawn it, and I've on purpose eliminated the capacitor so you know that no current flows there. That's the only reason I did it. I'm looking for that voltage. How many see this, okay? Everybody in the back? Now, how am I gonna get it? Well, I don't care how you get it. There's 5 or 6 different things you can do, probably to get the same result. For me personally, I see 6 and 12 in parallel, that's 4K. All right, I know that, I've worked around this stuff long enough. I got 4K here. Do y'all see those two are in parallel, class? How many do? All right, so if you don't mind, I'm gonna replace them just with 4K, all right? Now, do y'all see that at this point, it's almost trivial because it's simple voltage division, isn't it? Isn't this voltage here just 12 times 4 over 4 plus 2 or 6, right? So this is equal to 12 times 4K over 6, right? Or 8 volts. Do you agree with that, everyone? Show of hands here, how many see this? And I don't mean to make light of this, but if you've been doing this, by now you've developed a fair amount of confidence. Yeah, I got this. You should be saying, yeah, I got it. Now that's the voltage for t less than 0 across the capacitor. That's one of the things we need to know. Next, when the switch does its thing and opens for t greater than 0, follow me on this, what I'm going to say? I'm going to open this. So t equals greater than 0 opens, right? It's gone. Well, how much current can flow in this direction or that direction? None. As a matter of fact, that switch separated the entire part of the circuit with the voltage source apart from the other. Do y'all see that, class? How many do? And you can see by looking at this, are there any sources left to charge that capacitor after t greater than 0? None. So what is the final state of voltage on that capacitor? How many see it's 0? It must be. So now you know that I've got VC for t less than 0 equal 8. VCT goes to infinity equals 0. I need R Thevenin so I can get tau. Well, remember, this is the state of the circuit for t greater than 0, right? Everybody in the back, y'all see it? Just to really make my point, since the first part of the circuit is disconnected from the second right there, I want R Thevenin that would be appearing as if the capacitor was a load, right? How many see? It can only be 12K. You with me on that? So that's equal to 12K. Then what is tau, class? R Thevenin times C, right? So it's R Thevenin is 12 times 10 to the third. C is 150 times 10 to the minus 6. I really don't care how you do this. Normally what I do is say it's 1.5 times 10 to the minus 4. And that's 1.2 times 10 to the 4th. And I can see the minus 4th plus 4th cancel. And I have 1.2 times 1.5. Y'all with it? With me on that, class? And that would be tau. Do you all agree with that? I don't care how you do this one. Correct? And then, when you have that, what's the final step? Well, do I even need to solve for K2? I did, didn't I? Therefore, K1 is equal to the voltage at T equals 0, which is simply 8 volts. And I see that VC of T is 8 e to the minus T over this value of tau. Right? And then, I mean, that's it. And then to get I naught of T, what do I see? Well, it's VC of T divided by 12K. Is everybody okay with that, class? And that would be the steps that you would do. Now, that's, in my opinion, not a very challenging problem, but it's a good problem to make sure that you don't have any kind of, anything hidden that you're uncertain about. Are you with me? Okay, I want to do 34, and then I'll move. Yeah.
Oh, we're gonna go. I was just gonna ask about K1 again.
Okay, how do you get K1? Remember, this is K1 plus, really, I know it's 8 volts, but when I say VC of T is K1 e to the minus T over tau plus K2. K2 was 0, right? So if this is 0, you can see that K1 has to be the voltage at T equals 0. Y'all see that, class? Voltage across the capacitor, which is 8 volts. That's the reason I just plugged in.
And then K1, whenever that K2 isn't equal to 0, how do you solve it?
Do you remember what I just put on prior to that? I said that at T equals 0 would be K1 plus K2 would be the voltage at T equals 0, right? You don't remember that?
Yeah, I got it.
Okay.
K1 plus K2.
All right. Now, for 34. I guess I didn't give this one. I thought I did, but I don't know why I did. Unless it didn't post. All right. Okay, that's the problem. And I want the voltage across that capacitor for T greater than 0. So, you know the steps. First, I need VC for T less than 0 across that capacitor. Well, for T less than 0, now this is the thing. You can do this so many different ways. It's up to you what you feel comfortable with. I'm going to go ahead and just redraw it real quick down here. For T less than 0, if you look at this, I've got this current source of 2 milliamps in parallel with this resistor of 3K. Then I have that switch is closed. Here's where the capacitor is. I'm going to let it dangle like that and just call it VC, T less than 0. And over here, 3K and plus the minus 12 volts. One look at that tells you that you can do this part 3 or 4 different ways. Easy, right? You pick the one you like. I like source transforms, and then Thevenin if possible, or just go and see if you can get it right from Thevenin if you want. But for this right here, well, let's just think about it. How many see source transforms kind of make sense? Can't I do a source transform over there? Give me a show of hands if you see this. All right, yeah, and what would it be? 4 milliamp up in parallel with 3K. Do you agree with that, everyone? Yeah, I'm going to draw that just so you see it, all right? So I'm going to have want to make sure you see it. Everybody? How many see the 2 and the 4 milliamp can be added to 6? You see it in the back, guys? So I'm going to do that. So I'm just going to make this 6 milliamps. Get rid of this one. What next? Can you see it?
Combined resistors.
2 3Ks is 1.5K. Do you all agree with that, class, or 3/2 K? How many see that right there? They're in parallel. I'll make that 3/2 of a K. Agreed? All right, what's the voltage going to be across this resistor? And isn't it the same thing as the capacitor? What is that voltage? 6 milliamps times 3/2 K is what? 18/2 or 9 volts. Isn't it, class? How many see it's 9 volts? Far back, can y'all see it back there? 9 volts, sure. All right. Now I'm going to let the switch do its thing. It's going to go for t greater than 0 from here on out, or equal to 0. Y'all see when the switch changes state, it eliminates that upper segment, correct, class? How many see that? Y'all see that this entire section is disconnected from that. Everybody? Give me a show of hands if you do. All right. Now, I want the voltage across the capacitor as time goes to infinity. Before I just start drawing, I want you to ask yourself this. What does a capacitor look like as t goes to infinity for transient problems? Open circuit, right? Isn't that right? It looks like it's not there. So if this is an open circuit, what's the voltage across it? How much?
12 volts.
12 volts.
You guys do this to me just to aggravate me, don't you? You're Emmys, I know you guys. You're always prodding me. Here, I'll get them mad this time, watch. No current can flow, can it? If this is an open circuit, here's what I'm trying to say. And I want this voltage. It's open, right? How much current can flow? None, right? No current, no voltage, right? No voltage drop here. If there's no voltage drop here and I start the negative, I get an increase of 12 minus or plus 0 is 12 volts. Do you all see this, class? Give me a show of hands if you do. You guys do that on purpose. You got me. Beverly probably put you up to this. One of the Emmy pros. Anyway, are you okay with that, everyone? All right. Yeah.
So when you're measuring that voltage, is there not a current that runs through it since you are connecting the circuit?
We're at t equal infinity. It's a theoretical point, right?
Okay.
There's no current flowing, is there? At time goes to infinity, it's an open circuit, isn't it? If there's no current flowing, any other thoughts you're having are wasted. I mean, if there's no current flowing, there's no voltage drop. Fundamentally, it's like this. Think of a pipe and capping a pipe at one end, literally taking it off. And even if you have a long pipe before you get your pressure head, the pressure will be developed, will be the pressure head pressure across that gap because there's nothing flowing. All the pressure has to be developed there. Electrical pressure is voltage. Okay? Same thing.
Are there current sources in real life? Like, what is a current source in real life?
Yes, there are, but what happens is they're electronically monitoring the amount of current. Every time not enough current's there, they increase the voltage so that they sustain a certain amount of current. There is a limit. You can't have a current source into an infinite resistance. be an infinite voltage. But they're electronically monitored, they're not passive, like a battery is a passive, yes?
So if there had been another resistor and the T goes to infinity, like, would we have done voltage division to find that?
How can, I mean, depends where. If the resistor is in series, no, it doesn't matter. It doesn't matter if that's 3K or 3 million K, right? No current can flow, no voltage can drop. But if you have a resistor like this, then you have to, right? Because then current can flow around it, right? Y'all see that? It's pretty straight. Anytime current can flow, you can have a voltage across the resistor. But if current can't flow, it doesn't matter. You good with that? If current can flow, then you got a voltage drop. It's that simple. Huh?
It just determines how fast it'll charge your resistor.
Yeah, pretty much. That's exactly right. It's R Thevenin would be affected by it. Which brings me to my next point. What is R Thevenin?
3K?
Yeah, and that becomes a short. It's 3K. There's one resistor. Pretty good guess, right? Do y'all see that? So R Thevenin is 3K. Finally, what's tau? 3 times 10 to the third, right? Times, what was the capacitor? 300? Times 3 times 10 to the minus 4th, right? So that's 9 times 10 to the minus 1, or 0.9. And now you have your equation VC of t is equal to K1 e to the minus t over tau. I've got tau there plus K2. K2 was 12 volts, right? So how do I get K1 plus?
Negative.
I look at t equals 0, don't I? At t equals 0, I knew the voltage was 9. So 9 plus K1, or 9, sorry, equals K1 plus 12, or K1 is minus 3, isn't it? So the solution would be minus 3 e to the minus t over tau plus 12. And that's fine, okay? And that's that problem. Now, with the few minutes I have, I did want to cover that problem because it's a good problem. It causes you to think rationally about all this and apply your knowledge of circuits. So now, you just give me 5 or 6 minutes of time and your attention. By the way, is my grader here for you? He's not. Now we're going to look at the next element. There's only 2, the transient speeds. And that is an inductor. Just please do yourself a favor and be attentive here. You might learn something that will help you on the quiz. Here's what an inductor looks like. An inductor is just a bunch of wire wound on an axis, usually termed a solenoid. That's all it's called. And it stores magnetic energy. If there's a voltage across the inductor, created by a current through the inductor, the voltage on the inductor is given as L, the inductance, times di dt. Now here's really what happens. When things settle out, or don't change with time, for the capacitor, no current can flow, remember? For inductor, there is no voltage. They're short. So if you think about an inductor, what I just said, they're a bunch of wires spooled round and round, right? Doesn't it make sense if nothing's changing with time, it should be a short circuit? Doesn't that make sense? Sure. As a matter of fact, an inductor looks like a short circuit when things don't change with time, when they just settle out. For t less than 0 for transient problems, they look like short circuits, and as t goes to infinity, they look like short circuits. Are you with me on this, class? So when we have inductor problems, here are the steps. Actually, I need to put a problem down and show it to you, a real simple one. Let's see here. I'm gonna write the steps down, I'm gonna show you how it applies to this circuit. I wanna tell you one other thing too. You're gonna see a lot of similarity, and things will start clicking for you, if they haven't already. So when you're talking about inductor problems, the first thing you do is find the current through the inductor is time for time less than 0. That's just like we did for the capacitor. We found the voltage. Here we find the current. The second thing you do is find the current through the inductor as t goes to infinity. Instead of the voltage, now it's current. And the reason is voltage has to do with the energy on a capacitor, current has to do with the energy in an inductor. The third thing is you have to find R Thevenin across the inductor as if it was the load, just like the capacitor. You can literally remove it and see what the impedance is or the resistance is across that capacitor. And from here, then you get tau is equal to, and this one's different. Tau will be equal to L over R Thevenin. And in his book, or sorry, in your book, this is what it is. It's L over R Thevenin. All right, and then finally, the fourth thing you do is solve the equation IL of t is equal to some k1 e to the minus t over tau plus k2. I want to make mention, this is identical in form to what you did before. However, now you're looking for current, not voltages. Do you follow me? Current has to do with energy. Find the current for t less than 0. Find the current as t goes to infinity. Find R Thevenin just as you would if it was a capacitor. Either one are the same. And then you solve this. And the key thing is that these inductors look like short circuits when nothing's changing with time, but they look like open circuits the instant something changes, all right, changes state. In other words, it has an infinite impedance or resistance when something changes state, when the switch just trips. So let me go through this one to show you. Now, you all see this problem, right? For t less than 0, please listen to me. That switch is open, right? For t less than 0, that switch is open. Now, listen. I told you this thing would be a short circuit, right? Just look at this. If this is a short circuit and these two are in parallel, how much current will flow this way? 0. No current flows, all the current flows this way. You all see this? This would be for t less than 0 only. You all with me? Now for t less than 0, that switch is open. I got 100 milliamps. It has to pass through there, right? It's a current. I have 100 milliamps through there. Do you all see that? I didn't do any analysis other than describing what I'm thinking. Y'all with me on this class? Just think about what I'm saying. It's a very simple one, but there's enough uncertainty about how to do things that'll cause you a bit of, you might say, angst about this, all right? So I've got the current for t less than 0, all right? Now, when the switch closes, what happens? Anybody? Sure. When the switch closes, effectively all the current circulates there, doesn't it, class? It brings this point down to ground and it effectively isolates. You could literally take this resistor and put it right there. This source has no effect in that circuit for t greater than 0. Do you all follow me? How many do? People? With me in the floor back, guys? All right. What will the current be at t equal infinity? And give me a reason.
0.
Why though? You're right. There's no battery, no current source, right? It can't sustain that current because it will just decay to 0. So it's 0. Do you all see that, class? Now, once that switch is closed, I want R Thevenin across here, right? I'm going to erase it. I'm going to say, what is the Thevenin resistance across those 2 points? How many see the 6 and 3 are in parallel? Far back? All right. Yes, they would be 2 ohms. Do you all see that? That's the sequence you do these things in. Now, instead of opens, they're shorts. You with me? And when you do it, the only thing you do is solve for the current, like before for the capacitor, you solve for the voltage. With an inductor, you solve for the current. Don't worry about anything else they want. Then you find whatever they want. Follow me, class, you find the current in that inductor, and then any other thing they want will come forth from that. All right, that was the one thing I wanted to get through. What?
When you're finding arc level, and since the switch is closed, would the resistance just be closed?
Well, isn't this point grounded?
That's what I'm saying.
So wouldn't this be 6K on this side and parallel with 3K, or, I mean, 6 ohms on this side and parallel with 3 ohms on this? Huh?
No, I see, sorry.
Okay.
So then, how would be, 0.02?
Well, tau would be L, which is, 0.1 over 2.
So that's how, essentially 1 over 0.9 is now 0.02.
No, 1 over 2 is 0.05, right?
Yeah, sorry.
All right, guys, spread out at least one desk between you and your nearest partner on either side.